Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD student at IIT Palakkad. This is the week 12 of the live discussion section. In this section, we will discuss some of the theoretical questions and some of the problems. Okay, let's quickly start the section. Enough of the waiting. Let's start the section. Okay, so the first question is how many burners are placed in can annular combustor in gas turbines? Okay, okay. So so for a can annular okay, so for the can annular burner, it's not specified. It can be one or it can be more. Okay, so the answer is D. Not specific. One or more. Okay, multiple or single burners are evenly spaced in the combustor. The silo combustors are mounted internal to the gas turbine body. Okay, it's true or false. It's actually a false statement. Okay. So always remember silo combustor always mounted external to the gas turbine body. Okay. Mounted external to gas turbine body. Axial flow turbines are used in dash. Axial flow turbines are used in industrial gas turbines. Okay. So axial flow turbines. So the axial flow turbines used in industrial gas turbines. Okay. What completes a stage in turbine expansion? Okay. So what completes a stage in the turbine expansion? The answer is stationary blades row followed by moving blades row. Okay. Okay, so answer is C. Okay, what completes a stage in a turbine expansion? Answer is C. The stationary blades row followed by a moving blade row. Okay, this completes a stage. One stage that is that in the gas turbine or any kind of turbine, there can be multiple stages involved, and in that multiple stages, it means that there will be a stationary blade row. Okay, there will be a row of stationary blades. Okay, all stationary blades are there, and there will be one more row followed by a of what moving blades. Okay, there will be both stationary blades and moving blades are there in the stage of a turbine. Okay. Stationary blades followed by moving blades. What does uh, treat in a gas turbine stands for? Okay, TRIT. Okay. So the answer is A. Okay, turbine rotor inlet temperature. Okay. Answer is A. Turbine rotor inlet temperature. Okay, there is TIT also. Many times also occurred. Okay, we came across TRIT and TIT. Okay, TRIT is your turbine rotor inlet temperature, and TIT is your turbine inlet temperature. Okay. When at ideal condition, gas turbine engine use more fuel when compared to a reciprocating engine. Okay. Yes, it's a true statement. Okay. In the ideal condition, the gas turbine engine use more fuel than a reciprocating engine. Okay. Correct. Okay. So yeah, in gas turbine compressor, raise the pressure of air by dash times. Okay. Okay. So in gas turbine compressor, the air raises to a pressure of 30 times, which is extremely high. Okay, 30 times we can actually. This is the maximum value. Okay, maximum pressure rise possible is 30 times. Okay. Hmm. Gas turbine. Okay. The gas turbine pressure rise by what? 30 times. Okay. In the gas turbine compressor, the pressure rise is nearly 30 times. Okay. Okay, so let's go to the next question. Okay, in gas turbine is used to convert dash energy to dash energy. Okay, in the gas turbine there is always, you remember, the kinetic energy is always converted to the rotational energy. Okay, radial equilibrium theory assumes that flow is in equilibrium before and after the fluid entering the blade. Okay, so radial equilibrium theory assumes that flow is equilibrium before and after the fluid entering the blade, and this is actually a true statement according to the radial equilibrium theory. Okay, based on type of flow arrangements, gas turbines are classified into dash. Okay, there is, depending on the flow arrangement, there will be two types of flow always exist. One is the axial flow, one is the radial flow. So that means there will be two types of gas turbine exist. One is axial flow gas turbine, one is radial flow gas turbine. Okay. So the gas turbine, according to the flow type, is there is two types of gas turbine. One is the axial flow gas turbine. Okay. And one is the radial flow. Okay. Okay. Dash is developed when working fluid is passed through blade passage. When the working fluid passing through a what? A blade passage, there will be what? There will be friction. Okay. Okay. So there will be some loss of heat because when the fluid having some heat, okay, and those heats can be transferred to the blades, okay, and there will be chances of heat loss, okay. Okay, so and we just termed it as internal heat loss. Okay, so that's the reason why when we model these gas turbine blades, and or more specifically when we model the exhaust performance of a gas turbine, we'll need to model according to the, okay, uh, okay. So the working fluid when passes through the blades of the gas turbine, there will be a loss of heat, okay. uh, so, and thus the yes, so this working fluid is model, we have to actually more specifically the combustor will actually going to model in such a way that, or the exhaust of the combustor is modeled in such a way that the it cannot reach the melting point of the gas turbine blades, okay. There will be, otherwise there will be a melting of the gas turbine blades, okay. So yeah, and when this working fluid also pass, there will be chances of internal heat loss, okay. The kinetic energy of working fluid is dash the kinetic energy of case lossless flow. Okay. So the kinetic energy of the working fluid is greater than, okay, because of lossless flow means there will be some less losses are there. Less losses means the kinetic energy head will be also going to be less. Okay, so that's the basic of all this question. Okay, this question. Okay, so that's the reason the kinetic energy of the working fluid, more specifically the velocity of the working fluid is always greater than the velocity of the loss or less loss flow. Okay, So the ratio of actual velocity to the velocity of case lossless flow is called as dash. Okay. This we call is very commonly known as velocity coefficient. Okay. So velocity coefficient is equal to the actual velocity divided by the general or the ideal case where there is no loss. Okay. So the difference between actual enthalpy of working fluid to the case enthalpy of isentropic flow is called as dash. Answer is C. Okay. So the difference between the actual enthalpy of working fluid to the case enthalpy of isentropic flow is called as lo- losses. Okay. Okay. So delta H loss is equal to is the enthalpy of the working fluid, H working fluid minus H isentropic flow. Okay. The losses occurred due to the enthalpy change is caused due to dash. Okay, the losses occurred due to the enthalpy changes is caused due to dash. Losses in flow. Losses in flow caused due to friction. Okay. So the velocity coefficient is applicable for dash. Okay. This is a very good question. Why? Because this velocity coefficient is applicable for any kind of flow passage. Okay, which make this velocity coefficient more relevant for any kind of flow situation. Okay, so that's actually the kind of your importance of the velocity coefficient. Either it will be parallel, counter, or any kind of flow. Okay. So velocity coefficient can be applied for dash flow passage. Okay. So it's not specific like it can be applied for convergent, or it can be applied for divergent, or it depends on the flow passage. Okay. The answer is D, because it can be applicable for any of the flow passage. Okay. So the velocity coefficient applied for any flow passage. So now, okay, so velocity coefficient can be applied for dash blade passage. Okay. Okay, so answer is D. Okay, any of the flow passage. Okay. The blade profile losses for a diffuser blade depends on dash. Okay. Depends on the kinetic energy. Okay. Okay. So the blade profile loss for a diffuser blade depends on the kinetic energy. Okay. Okay, the blade profile losses are dash losses. It's actually small losses. Okay, of the stages of a turbo machine. So the blade profile loss blade profile loss is the small losses of the stages at turbo machine. Okay. A turbine having alternate blades and nozzles is called as dash. Okay. A turbine having alternate blades and nozzles is called what? Impulse turbine. This is the definition of an impulse turbine. Okay. Okay. So what is the advantage of if I will arrange the blades and nozzles in an alternate manner, then it will decrease. So the pressure loss will decrease. Okay. So the multi-stage arrangement of turbines is called as what? It's called compounding. Okay. Okay. So the multi-stage arrangement of turbine gives the advantage of decrease in pressure loss and decrease in velocity loss. Okay. Called as compounding. Okay. mass here. So the compounding dash efficiency at low speed. Okay. So the very good advantage of compounding is that the efficiency is always high at also with although it's in the low speed operation. Okay, mostly the speed increases, the efficiency is going to increase. Okay, but although in the low speed also the efficiency of the in the case of compounding is also high. Okay, or increases. Okay. In pressure compounded turbine, the moving nozzles are followed by turbine blades. Okay. It's a false statement. Okay. It's actually kind of reverse. The fixed nozzles followed by the moving blades. Okay. The fixed nozzle followed by the moving blades. Okay. So the in pressure compounded turbines flow passage is from dash. So in pressure compounded from fixed nozzle to moving blades. Okay. The pressure component turbine, the flow passage is from fixed tip nozzle to moving blades. Okay, read this question and try to solve. I think you have tried the question. Okay, let's start solving the problem. So the question is a radial flow turbine of the following geometry is tested under the design conditions with a pressure ratio of P01 by P3 is equal to 2 and at the inlet temperature of 1000 Kelvin. The work output after the allowance has made for mechanical losses of 45.9 kilowatt when the rotational speed is 1000 revolution per second and the gas mass flow rate is 0.322 kg per second. The rotor inlet tip diameter is 12.7 centimeter, rotor exit tip diameter is 7.85 centimeter, hop tip ratio at exit is 0.3, nozzle efflux angle alpha 2 is equal to 70 degree, rotor vane outlet angle beta 3 is 40 degree. Okay, separate test on the volume to nozzle combination showed the nozzle loss coefficient. Okay, lambda n to be 0.07, the turbine isentropic efficiency eta t and the rotor loss coefficient gamma r are to be evaluated from the results. Okay. That means the eta t and the gamma r we need to evaluate from it. Okay. So let's start solving. Okay. So let's apply the formula quickly. So the T naught 1 minus T3 dash is equal to T naught into 1 minus 1 by P naught 1 by P3. Okay. To the power gamma minus 1 by gamma. Okay. So just substitute the values and find out the temperature difference. 1000 into okay. So let's find out the work done W. Okay. So T naught 1 minus T naught 3 is equal to W by m dot into Cp, which is 45.9 divided by 0.322 into Cp is 1.148. All things are given. Just substitute and find out the value of temperature difference. Okay, 124.2 and it is 159.1. Okay. So to find out the eta t, what we will do, we'll just take the ratio. Okay, eta t is equal to what? T naught 1 minus T3 dash T3 prime divided by T naught 1 minus T naught 3 is equal to, sorry, it's a reverse. T naught 3 Okay, so this is 124.2 divided by 159.1. Okay, you will take the ratio, you will get 0.781. Okay, this is the answer. So now if you will find out the ratio of R3 by R2, okay, let's find out the R3 by R2 ratio. Okay, so R3 by R2 is equal to 0.3 into 7.85 plus 7.85 divided by 2 into 12.7. Okay, all these values are 7.85. rotor tip exit tip diameter given. Okay, your rotor inlet tip diameter also given. Okay, and 0.3 is a hop tip ratio at the exit. Okay, all things are given. Okay, to find out the ratio of R3 by R2. Okay, so if you solve it, you will get the value as 0.402. Okay, so now let's find out the formula of, let's substitute in the formula of eta t. Okay, implies eta t is equal to 0.781 is equal to 1 plus 1 by 2 0.402 square into cot square 40 plus gamma r cosec square 40. Okay, plus 0.07 cosec square 70. Okay, inverse. Okay, so if you solve it, you will get the value of gamma r, because the gamma r is the only unknown here. Okay, solve, you will get the value of gamma r as 0.64. Okay, which is your answer. Okay. Okay, let's solve this question. This is the last question of the section. Okay, a single stage gas turbine operates at its design condition with an axial absolute flow at entry and the exit from the stage. The absolute flow angle at the nozzle exit is 70 degree. At stage entry, the total pressure and the temperature are 311 kilopascal and 850 degrees Celsius respectively. The exhaust static pressure is 100 kilopascal. The total to static efficiency is 0.87 and mean blade speed is 500 meter per second. Assuming constant axial velocity through the stage, determine the specific work done, the Mach number leaving the nozzle, the axial velocity, the total to total efficiency, and the stage reactions. Okay, in the right side the diagram already given for of the stator nozzle and the rotor. Okay, let's start solving. The TS diagram also I have drawn. Okay, this is the TS diagram for this question. Okay, so let's quickly calculate the things what's required in this question. Okay, so the first thing they ask is the specific work done. Okay, they want the specific work done. Okay, let's find out the specific work done. Okay, so we know one thing. What is the total to static efficiency? Okay, so the total to static, so eta Ts is equal to Wt divided by Cp into T01 into 1 minus P3 by P01 to the power gamma minus 1 by gamma. So here we need to find out the specific work, which is Wt. Eta Ts into Cp into T01 1 minus P3 by P01 to the power gamma minus 1 by gamma. Okay. So yeah, all the things are given. Just need to substitute all these values and find out the Wt. Okay. So 0.87 into 1148 into 11, okay, 1123 okay. Okay, this is your answer. Okay. Okay. So what is the second question? The second question is we need to find the Mach number leaving the nozzle. Okay. Okay. We need to find out the Mach number, and that means M2 you need to find out. Okay. Okay. So at nozzle exit, M2 is equal to C2 by square root of gamma R T2. Okay. Here for this configuration, the CW3 is equal to 0, Wt is equal to U into CW2, CW2 is equal to Wt by U. Okay. So because Wt you already find out from the A bit. Okay. Just substitute and find out, because we find out what Wt is what 276 kilojoule per kg. Okay. Substitute you already given in the question. Okay. In the question it's given 500 meter per second. Okay. Is the mean blade speed, that means U given. Okay. Just substitute and find out the value of CW2. 276 into 10 to the power 3. I converted into joule per kg divided by 500 is equal to 552 meter per second. Okay. So then you find out the C2. C2 is equal to CW2 by sine alpha 2 If you solve, you will get the value as 588 meter per second. Again, T2 is equal to T01 minus half C2 square by Cp. If you solve, you will get it as 973 Kelvin. Okay. Now we have everything to find out M2. M2 is equal to now 588 divided by square root of 1.33 into 284 into 973. So M2 is equal to M2 is equal to 0.97. Okay. So next go to the C bit. What is the axial velocity? Okay. C is the axial velocity we need to find out. Okay. CA equal to C2 into cos alpha 2. Okay. If you solve it, you will get the value as 200 meter per second. Okay. The next bit is the total to total efficiency. Okay. So the total to total efficiency so 1 by total to total efficiency is equal to 1 by total to isentropic efficiency minus C3 square by twice of the work done. Okay. So everything we know, just substitute and find out. Okay. 1 by 0.87 minus 200 square divided by 2 into 276 into 10 to the power 3. Okay. So if you solve, you will get this value as the total to total efficiency as 0.93 or 93%. Okay. Next, let's find out the degree of reaction. Okay. Okay. Let's ask the stage reaction. Okay. The stage reaction they asked, or the degree of the reaction they asked. Okay. So oh, Okay, so from the velocity triangle, we can find out the beta 3 and beta 2. Tan beta 3 is equal to u by Ca, and tan beta 2 is equal to tan alpha 2 minus u by Ca. So the Rx is equal to 1 minus 1 by 2 Ca by u into tan alpha 2. So if you solve it, 1 minus 200 into 0.2745 by 1000. So if you solve it, you will get Rx as 0.451. So we solve all the bits of the question. Okay. So thank you very much for attending the section. If you have any doubts, you can ask in my comment section of my channel. Sumit Sagar Hota is my channel name, YouTube channel name. Okay. And regarding this lecture 12, okay, there will be one more section tomorrow. Okay, of the summary section. There I will solve some of the important problems of the lectures, of the sections. Okay, various sections. Okay, thank you very much. Have a nice day and good night.